Welcome back. Today, we're going to talk a little bit about how we build operators in this formalism, and maybe a little bit of the mathematics behind why we chose these operators, and then how to represent operators as matrices. So I want to go back to a definition, and I will say in some quantum mechanics courses, this is sort of the thing that they say on the first day, right? But it's important for us to build a little bit of that physical intuition before I start using some of these fancy words. But I'm going to talk more generally now about some operator, which I'm going to call capital O for this slide. And that operator, remember, is kind of, it acts like a measuring device, right? All the operators we've seen so far have actually been an experiment, right? It's been some sort of apparatus that I can use to actually take a measurement of some physical system. And therefore, the intuition that we've been building over thinking about states coming out of these systems reminds us a heck of a lot of the whole eigenvalue, eigenvector problem, okay? And that's why I think it was important to talk about the apparatus before we developed the mathematics for the apparatus. So this operator O, I think about in my mind as actually being some piece of equipment, right? Or some table that can actually make a measurement. Now, we don't always have that table, right? Sometimes this is a thought experiment rather than a real experiment. But in principle, what I see in this operator is the ability to take some measurement. And then all of the possible measurements that come out of it are really the eigenvalues of that operator, right? They are the pure, they are the results of the measurement. And therefore, for every eigenvalue, every result of the measurement, I have some eigenvector, which represents the pure state that corresponds to that measurement. Right? And so the operator is the device that defines all of my pure states. It defines my eigenvectors, and therefore it defines my eigenvalues, right? And it sort of brings this picture together that I have an operator that has a set of eigenvalues. Those eigenvalues are the measurements, and I have a set of eigenstates, and those eigenstates or eigenvectors are the pure states of the system. And those are the things that I can get out at the end of the day. Now, of course, when I think about what are the properties of these eigenvectors and eigenvalues, one thing really stands out, and that is that even if my eigenvectors are somehow, living in the complex numbers, the measurements that I take, right, the actual measurements that I make in the lab, actually end up having to be real. Okay? And so what we want mathematically, or what we are going to demand from our mathematical formalism, is that we restrict ourselves to the types of operators that will actually give us real eigenvalues, right? These eigenvalues have to be real. They cannot be complex numbers in order to be genuine quantum mechanical operators. And it turns out that there's a mathematical condition, and that's called the Hermitian operator. And the Hermitian operators are guaranteed to have certain properties. But first, I think I'd better tell you what it means to be a Hermitian operator. And at first, this is going to sound a little, what's the right word? Unsatisfying, because a Hermitian operator is defined to be that its Hermitian conjugate, which is denoted by the little dagger, is equal to itself. Okay, not helpful. The Hermitian conjugate means that I take that matrix, that operator matrix, and I transpose it and I take the complex conjugate, right? So I do two operations at once. This is exactly the same thing that I feel when I take a ket vector and I turn it into a bra vector, right? I take its complex transpose. I'm doing the same thing here, but I'm doing it with the entire matrix, right? And so we're going to call that the Hermitian conjugate. If the Hermitian conjugate is equal to itself, then it's a Hermitian operator. And if it's a Hermitian operator, that guarantees mathematically that the eigenvalues of that system are real, and that the eigenvectors of that system are orthogonal, right? And now that's a beautiful result, right? As far as physics is concerned, I wouldn't want anything more from my physical system other than to have a orthogonal set of eigenvectors, because that's going to build a basis, right? And a basis that has that's orthogonal, right? So that I have this that I can, when I do inner products of bras and kets, I'm only going to get out ones and zeros, right? I mean, that's great, right? That's exactly what I want from a set of vectors, and I'm guaranteed to have these eigenvalues that are real, right? And so these are exactly the two things that I want. And so it's not surprising if we have a whole set of operators that are guaranteed to give us this property, we might as well try to build our mathematics in that set of operators, so that way we have these two great things coming out of it, right? A good set of basis vectors, which are orthogonal, and if I normalize the basis vectors, which we talked about in a previous video, then they're orthonormal, right? And that I have eigenvalues that correspond to real measurements. And so in your mind now, when you see these quantum mechanical operators, you say to yourself, well, the operator is the device, and when I use that device to measure, I'm going to end up by measuring some eigenvalue, right, of that Hermitian operator. And that is what a measurement means in a quantum mechanical sense, right? That when we take the measurement, we're looking at a pure state, right? That's what comes out of one of these devices, and therefore I can associate the measurement of that quantity with the eigenvalue of that particular pure state. Okay, so now what this means is that if I take this definition to heart, right, that an operator defines a set of eigenvectors, right, then I can use those eigenvectors to build a basis for all possible vectors in that space. Okay? That's an awfully abstract way of thinking about it, but I think we're there, right? That when we have a quantum mechanical state, right? I know that it's built up of a sum over all of the different pure states with probability amplitudes as the coefficients in front of each one of those terms. And that idea brings us very much back to this idea in linear algebra, or this idea that we talked about in 245, where I'm able to use that basis, right, which is defined by my set of eigenvectors, to build a matrix representation of the operator. And I want to say that again, and this time I'm going to say it in just a few different words, because I think it's really important to know when can we take an operator and write it as a matrix, right? Because this Stern-Galich experiment that we talked about last week, right? It's always going to be the Stern-Galich experiment. It doesn't care if I know linear algebra or not, right? It's going to give me two different measurements of the z component of the spin, right? It in a way, it doesn't care about the mathematics that we're going to use to describe it. And therefore, if I want to describe it as a matrix, if I want to describe it in some way where I can use linear algebra in order to describe the system, then I need to add to that operator some basis that I can use to represent that operator, right? I have to have the basis in order to write down what the components of that matrix are, right? And that's an idea, again, we talked about it a little bit in 245, but it's so central to building these operators, right? And it's something that a lot of textbooks on quantum mechanics sort of sneak by you and hope you don't notice them saying really fast is, well, this is the SZ operator and the basis of the blah, 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 right? That in order to write down the matrix for an operator, I have to think about that operator in terms of some basis. Right? And so I can write down a general form, and maybe it's helpful for me to write it down once in sort of its full glory here, right? But if I think about having some operator A, and I want to find out, like, what literally are the different numbers that go in the matrix of A, then I can find any particular entry. So A sub ij corresponds to the ijth component of that matrix. Remember, the first index is going down the elevator, right? And the second index is going across the hall, right? So I'm on the ith floor down, and I'm on the jth door over, right? That is defined to be this fun product of the of the ith eigenvalue, right? The ith eigenvector with A with the jth eigenvector. Okay? And this really is the definition for what number goes in that particular entry of the matrix. Okay? And this operation seems really hard to do, although it's kind of pretty to look at, right? Because I have this, I've constructed a beautiful scalar, right, by squishing my operator in between two of my eigenstates. And we'll find out in a moment that sometimes this is really hard to do. Sometimes maybe we can't even do it without having some extra information. But it does give us this idea that the entries of that matrix come from both the operator and the basis, right, that we're using to describe the operator. So let's try it for the SZ, right? This is the operator that we've been using for the entire class. This is the original Stern-Gelick experiment. And the reason why we want to use that is because we know already that operator has defined for us two different pure states, right? The plus state, spin up, and the minus state, spin down. And so I'm ready, in a sense, to take this operator and I'm ready to write it down as a matrix, okay? And why am I ready to write this particular operator as a matrix? Well, I've written out two of the different components, right? So here, let me add some notations here. So I like to think about, this is 1 and this is 2 and this is 1 and this is 2 because those are the first row and the second row and the first column and the second column. If I look at this, the 1, 1 component, right, that corresponds to sandwiching. I think that's a technical word, sandwiching my operator in between two different spin-up states, right? In between those two eigenvectors. And if I look at this, I say, well, this thing here, which looks complicated to do, is actually, well, the plus state is an eigenvector of the SZ operator, right? And therefore, if I take SZ and act it on that state, right, then I know what the outcome is going to be, right? Because SZ acting on the plus state is going to give me h bar over 2 times the plus state. That's the definition of an eigenvalue. Right? And this is why it's easy, quote unquote, to write down an operator in its own basis, right? Because they're eigenvalues, they're eigenvectors of that basis. And so it feels a little like cheating, but I really have no problem calculating this thing because it's just that operator, which I don't know the representation of, just turned into an h bar over 2. Right? So let me erase this so that I have a little bit more room. And what that means now is that thing that was hard to do because there was an operator squished in between two states turns out to just be h bar over 2 times plus plus, which is of course just h bar over 2 because it's a beautiful orthogonal set of eigenvalues, right? And that the plus state dotted with the plus state is 1, right? Because I properly normalize my eigenvectors. and that seems like it took a lot of states to get out an h bar over 2, right? Or a lot of steps to get out that h bar over 2. But it shows us how we now have that number that's going to go in the upper left part of this matrix because I've used the fact that the basis are the eigenstates of the operator that I'm using. I feel like I say the words eigen and operator. Anyway, so this first term then is just going to be h bar over 2. All right, let me do one more. Okay, so let me get rid of this so that I can do another one, right? This, of course, SZ acting on the minus state, well, that's going to give us minus h bar over 2, right, times minus. That the minus state has the other eigenvalue. And then I have a plus on the left. Well, the the minus h bar over 2 comes out, and I'm left with plus minus, and this would be a great time for me to ask, and what is that? Right, that's 0, right, because plus and minus are orthogonal to each other. So I can do all 4 of these, right? And now I encourage you to do the other 2 the way that I've done these, right? And then I would get all 4 components of a matrix, right? And exactly those 4 components are the 4 components of the matrix for the SZ operator in the basis of the SZ eigenvectors, right? And then it looks like, well, it's a matrix, right? But it's a pretty simple matrix, right? Only the diagonal parts exist, right? Because of these, because of our Kronecker deltas that we get from doing the dot products of states with themselves. And I end up with this really nice, really simple form for what this vector looks like. And in fact, if you think back to maybe what you know about eigenvectors, every time I have a diagonal matrix, right, I know that the eigenvectors are the different components of that matrix, right? In fact, if we did some work on this, we could also find out what the eigenvectors look like in this basis, and we would find out, that they're 1, 0, and 0, 1, right? They're good states, right, for us to have here. Okay, and that's how, in principle, you always can write down the components of a matrix if you know what the eigenstates look like. Well, that's great for SZ, but what about operators like SX? Right? Now, this is another Stern-Gerlach experiment. And how we've been talking about this, sure, it has its own basis, right? Plus x and minus x. But we've always been trying to represent that basis. We've always been trying to represent those vectors in the basis of SZ, right? We've been talking about one sort of fundamental basis, and I don't know why I call it fundamental, because it was absolutely arbitrary to choose the z direction as our definition of plus and minus. But what if I wanted to write down the components of the SX operator in the SZ basis, right? Well, I'd have to do things like this, right? So I've set up this table again. The component here in the upper left is going to be the plus state Sx plus, and I try to do what I did last time, and I say, well, do I know what Sx acting on plus is? Well, is plus an eigenvector of Sx? No, right? It is not an eigenvector of Sx. We shot the plus beam through the Sx Stern-Gerlach experiment, and we didn't get out one pure state. We got out 2 different measurements, right? And therefore we know that the eigenvectors of the SZ operator are not the same as the eigenvectors of the Sx operator. And since the eigenvectors aren't the same, I can't do this operation, right? Or from the get-go, I can't figure out what this is. Either I have to do a lot of experiments where I shoot different things into different. I have to do a lot of things in order to figure out what these states look like. Or I could take a course on group theory and come up with some idea for how do I rotate these states to get another matrix that shares the properties of the Sx operator. Okay, and this feels a moment like a cop-out, but it's not really too bad, right? I know that I'm looking for certain properties in this other matrix. Therefore, I'm developing a mathematical model, and I'll use that mathematical model to test whether or not it's consistent with my experiment. There's absolutely no problem with that, and so that's the thing that we want to do, right? So group theory tells me that there is yet another 2x2 matrix, and this one looks like this: h bar over 2, 0, 1, 1, 0. And we ask ourselves, well, is this matrix, what are its eigenvectors and what are its eigenvalues? And even though this problem now, the previous problem seemed easy, although it turned out to be rather hard and sometimes not possible. This problem seems hard, but it uses exactly the processes that you know, right? I mean, you know how to take a matrix and find what its eigenvalues and eigenvectors are. And I'll have a little mini video to remind us on how to do that and how to do it in Mathematica. But for the sake of what we're going to talk about right now, I'm just going to assume that we perfectly remember how to take a 2x2 matrix, find its eigenvalues and eigenvectors. And bada bing, in this system, I get two different eigenvalues, right? H bar over 2 and minus H bar over 2, which are the two values of the x component of the spin that I got from my Stern-Gallic experiment. This is consistent with the experiment in that way. And I get two eigenstates, which I can write in terms of the SZ basis. And lo and behold, these are the same states that we looked at, before. And the probability distributions are consistent with what I get from the Stern-Gallic experiment, right? And so we've tied that final loop of science together. That if we postulate that this represents the X Stern-Gallic experiment, well, it's totally consistent with the results that I get from that. Okay. Now you can also imagine there's in addition to this there's an SY matrix, and probably we're going to do some work with that in class and on your problem sets. Okay, but now what this has done for us is it's shown us that in this same two-dimensional system, I have at least two different bases, right? The basis that's defined by the SZ operator and the basis that's defined by the SX operator. And they both have two different outcomes, two different measurements, and they all mix in with each other, right, in this beautiful way. And I think that's the point to pause here, right? In that each of my Stern-Gallic experiments has two possible outcomes. But the two possible outcomes of the z direction are linear combinations, are mixed up with the two possible outcomes of the x direction, which are mixed up with the two possible outcomes of the y directions, right? That system, it's a two-dimensional system that has at least three different bases in it, right? It really looks like a beautiful problem of taking a measurement in this vector space. Really is about how are you gonna rotate those axes in the two dimensions that I have. As a warning, like we did in 245, what I've done here is really kind of the simplest possible system. Now, it's also true that it's one of the most interesting systems, and it has a lot of beautiful phenomenology. In fact, the idea of these two-dimensional systems are still the foundation for what people talk about for quantum computing, right? And you should talk to Professor Schumacher more if you're interested in that. But this two-vector system, this two-state system, in and of itself is really, really interesting. But it's sort of the lowest possible dimension discrete number that I can come up with. And so you know from your experience with physics courses that there are probably going to be these spaces that can be represented as discrete and finite, right? That I have only a certain number of terms, and therefore my vector space has dimension 2 or dimension 3 or dimension 5, and I can write things down as beautiful compact vectors. Well, I'm also going to have these spaces where, even though it's discrete, there's no limit, right? There are an infinite number of eigenvectors to the system, right? And therefore, I can kind of think about it as a matrix, but maybe some of my intuition breaks down when I get really far into that matrix. And so those are the sort of countably infinite sets, and these, of course, are the things you saw in modern physics when you first looked at quantum systems, right? Or you think about atoms and their energy levels, right? There's an infinite number of those, even though they're discrete. And then finally, we probably will also get into the place where we're going to use this formalism to talk about continuous vector spaces, right? And then even our idea of kind of the matrix falls apart, although, to be honest, almost every physicist goes back to that idea of a matrix, even when we're talking about continuous systems, which is why I think it's a good place to start. Okay, so your take-home messages are Hermitian matrices are the measurement devices. And the eigenvalues are the measurements, and the eigenvectors are the pure states. I have this formula to write down how to calculate the matrix in terms of a given basis. This is really easy if the basis is the basis defined by the eigenvectors of the system you're studying to begin with, although in principle I can do it for any operator. And we can find out if the reverse problem is true. If I know what the matrix of the operator looks like, I can somewhat more easily calculate what the eigenvectors and eigenvalues are, and therefore I can calculate what the pure states are and what the measurements are going to be. All right, see you next time.